Welcome back to Physics 4480. The topic today is to start our discussions of many-body perturbation theory. Many-body perturbation theory is one of the central approximations to the exact solution which we exposed through FCI theory, or full configuration interaction theory. Now, full configuration interaction theory gives us the exact answer in case we can represent all degrees of freedom into a Hamiltonian matrix. Now, normally we cannot use an infinite space in order to represent our basis, which means again that we have to make some truncations. So even on FCI calculations, although we can get all eigenvalues and eigenvectors, this Hamiltonian matrix, which we end up diagonalizing, is the result of a truncation in a single particle basis. And since we are using a single particle basis to construct a many-body basis, this means that we end up also with a truncated many-body basis, which we can further truncate. And there are many different approximations to FCI theory. And we're also going to bring back some of the Hartree-Fock results, which we discussed earlier. We're going to start us with reminding ourselves about full configuration interaction theory. And we are going to start with a simple two-level problem. And this simple two-level problem is going to serve us as a kind of entry point to many-body perturbation theory. And as you will see, even through this simple two-level problem, which translates into Hamiltonian matrix of dimensionality 2 times 2, we can illustrate many of the basic properties and features of many-body perturbation theory. You will also encounter this simpler problem in the disguise of an exercise a little bit later. But let's switch back to the whiteboard and remind ourselves about FCI and Hartree-Fock theory. So what follows now is a quick reminder of some of the basic ingredients of FCI theory and what we ended up with after we had diagonalized. So one of the things which we end up having to do is to expand. And if we now focus on the ground state, we expanded this ground state in terms of a set of orthogonal and normalized basis states, many-body basis states, which we label by a phi of I. And we had an expansion in terms of this basis, which in principle should be infinite because we often have, we actually by essentially in all cases, we have an infinite single particle basis, which we use to construct a many-body basis. Then we have some overlap coefficients, C of I. And then we had this basis of orthogonal Slater determinants if we're dealing with a system of fermions. So this basis is an orthogonal and normalized basis, which also means that when we calculate the overlap here between two of these states, which we normally represent by a Slater determinant, this is just given by a Kronecker delta. Now, one of the things which we did was to rewrite this expansion in terms of particle-hole excitations. So let us quickly remind ourselves about that. It means that this expansion was something which we wrote out in a more general way with an uppercase P, where P now represents all possible particle excitations, and H obviously hole excitations, which means that PH here represents all possible particle hole excitations. And then we had the overlap coefficient, CH or P, and we could have the ground state itself, which is this represented by an ansatz phi 0. And in that case, we have a zero particle, zero hole excitation. And we had the state, which now is represented by a set of Slater determinants. And the way we rephrased this was in terms of an ansatz for the ground state, where this ansatz is now constructed using something which is called intermediate normalization, which we discussed a little bit earlier. And then we have a sum over all the different particle hole excitations. So we have a one particle, one hole excitation, where we have a coefficient CIA, and then we have the Slater determinant phi IA, which represents a one particle, one hole excitation. And then this continued till the final n particle, n hole excitations. In case we have n particles, we can make n particle, n hole excitations. So let's just quickly remind ourselves of the way these summations look like. So we have an A, B, and IJ. We have a coefficient, and these coefficients are the overlaps between a specific Slater determinant and the exact ground state, which we obviously don't have. So we then ended up with these states, and this continued all the way till what we called for n particle, n hole. Now, these states, like a one particle, one hole state, is given in terms of the creation and annihilation operators, where the A, B, C, etc. stand for states above the Fermi level, and the I, J, K, L, etc. stand for states below the Fermi level. And normally we, in a sloppy way, we often call them for just hole states. And these operators are now acting on the reference vacuum state, which in our case is represented by particles filling all the states up to what we have defined as the Fermi level. And similarly, the state phi I J A B is then given in terms of an anti-symmetrized chain of operators of AJ, AI of phi 0. And this is a one particle, one hole state, and the next one is a two particle, two hole state. And we can continue in this fashion and build up three particle, three hole, four particle, four hole, etc., etc. Now, in FCI, what we found is that these coefficients, Cij, AB, or in general CHP, representing the overlap between one of these states, like this state here with the exact ground state, which we get from diagonalization, then these coefficients which we have here, theCij's, etc., they are the eigenvectors which result from the diagonalization of the Hamiltonian matrix. So if we can diagonalize, then we do have the exact eigenvectors and eigenvalues for that specific Hamiltonian. Now, one thing which we did then was to look at the matrix elements for the Hamiltonian, and we constructed then the overlaps between phi 0, the unperturbed state, and H and psi 0. And when we did that, what we found was that this was given by phi 0 of H, phi 0. We are just looking at the value of psi 0, which is now being inserted in terms of these different terms. So we have a plus, an IA, and then we have this coefficient CIA. And what we got then was the overlap between phi and H and phi of IA. And in case our Hamiltonian is given by at most two-body operators, then this expansion, which in principle should have included now three particle, three hole, four particle, four hole, etc., etc., this terminates exactly at the level of two particle, two hole excitations. And then we have the Cij of AB, and then we have the overlap between the exact state and phi I A J of B. And this is equal to the ground state energy. Now we could play this exercise with other states than just psi 0, which is now assumed to be the lowest lying state, which we normally call the ground state. But we could have looked at excited states as well and played the same exercise, which you see here. Now, the term which we have here is a term which we label as the reference energy. That means the energy which is calculated with respect to a reference, a reference state, which in our case is this Slater determinant phi 0. Now, it's common then to reshuffle these terms so that we could rewrite E0 in terms of phi 0 and the expectation value of the reference state. And this is a term which we call E0 ref, the reference energy. And we call this for the correlation energy. So these are the contributions to the energies which are beyond the expectation value of the reference state. So this quantity here is called the correlation energy. And then we found that this is given by the sum over IA, CIA. And when we calculated the specific matrix element, this was given in terms of this operator F, which we also label as the Hartree-Fock operator. So this quantity which we have here is then simply given by A, and then we have H0 of I plus a mean field contribution where we sum over all states below the Fermi level. And then we have an A of J, of V, of I, of J. And these are anti-symmetrized matrix elements. And then we have the next term, which is now given by the sum over two particle, two hole excitations. And we have a Cij of AB. And then we get a matrix element of AB, of V, of Ij here, anti-symmetrized. Now, in case we have performed the Hartree-Fock calculation, then what we found is that this contribution here is actually set to 0. Now, what we can do now is that we can now insert these specific so-called matrix elements, which are actually integrals, but we label them as matrix elements. And we can multiply them with these coefficients, which we have here. Now, this is a clumsy way of getting this energy because when we diagonalize, we actually get the energy. And there's no point in doing this exercise. However, the reason why we bring this up now is obviously one, there's a link to Hartree-Fock theory, which means that this term is exactly equal to 0 in case we have performed the Hartree-Fock calculation. And then we would just be left with this term. Now, secondly, what we are going to do now is to show how we can actually obtain these coefficients from many-body perturbation theory. And if we are going to do many-body perturbation theory to second order, we are going to see that this coefficient here is simply going to be given by the matrix element Ij, V, AB, anti-symmetrized, divided by the single particle energies, epsilon I, epsilon J, minus epsilon A, minus epsilon B. And this is going to be perturbation theory, PT, to second order. We're also going to see that this term, which we have here, this one, is going to be equal to I and the same term F of A divided by epsilon I minus epsilon A. This is the second order perturbation theory. Now, when we go to higher order perturbation theories, these expressions are going to be more complicated. But the whole recipe which we are going to develop now is a recipe by which we can calculate these terms with quantities which are known. So we are assuming now that we have pre-calculated these quantities or that we can easily calculate them. And similarly, we also have a table or a recipe by which we can calculate these single particle energies. This means that order by order in perturbation theory, all the terms are terms which we can evaluate. So we have a recipe for them. And that means that we can then approximate the energy which you see here, this correlation energy, by different terms in perturbation theory. Now, it shouldn't be unexpected that if I can do perturbation theory to infinite order, I should recover the expressions which I would get if I diagonalize. So just to remind you, if I can diagonalize, then I do obviously obtain these quantities. I do obtain the exact energy diagonalized from a specific Hamiltonian matrix, which is defined by a specific set of basis states. However, if this is too complicated, if my Hamiltonian matrix is too large and unwieldy for exact diagonalization, then we have to find approximative schemes. And we have already encountered Hartree-Fock theory as one of the approximative schemes. Our next approximative scheme now is many-body perturbation theory. And we can use a Hartree-Fock basis as a starting point for many-body perturbation theory. And if we're going to do that, then a term like this one would be exactly equal to 0. So Hartree-Fock theory is often used as a kind of kitchen item. This is another way to look at it. And this is then inserted into so-called post-Hartree-Fock methods. That means that we are going to build up this correlation energy by constructing approximations to these coefficients. Now, this expression, which you see here, is also one of the starting points for when you do coupled cluster theory, which is another post-Hartree-Fock method we are going to discuss. And coupled cluster theory gives us another recipe for finding these coefficients. Similarly, if you're going to do Green's function theories, we will have another recipe for finding these coefficients. Many-body perturbation theory, from a mathematical point of view, is nothing but a Taylor expansion around a specific energy. And we are going to see that through a very simple example. So in order to build up our intuition about perturbation theory and the mathematics of it, which in essence is a Taylor expansion, we're now going to look at a simple two-level problem. And this simple two-level problem is now set up as follows. So let's take a look at it and use this as an entry point for our discussions of many-body perturbation theory. So this simple problem here is now defined by a Hamiltonian, which contains a part which we're going to call an interacting part and a non-interacting part, as before. So this is just a sum over all the possible single particle states. It has an energy, epsilon p, so this is just the integral which we have been listing before. And it's given by creation operators and annihilation operators as before. And we are going to define an interaction term which has a constant g, and then it sums over p and q, and then we have an AP, so it's still a one-body operator. Then what we have is that this basis which we have chosen, the basis P and Q, etc., is assumed again to be an orthogonal basis. So when we calculate the expectation value of this specific operator H here, of a state with a state Q, this is simply going to be given by a delta PQ multiplied with this energy epsilon P. And in our case, we are going to assume that we have only two such states. So we are going to have two particle states, or just two states. They don't need to be single particle states. They could actually be many-body states. And we assume now that there's an epsilon 1 whose energy is less than epsilon 2. So this is going to define the ground state of the system for the unperturbed case. And later, this is for later, we are going to define a state P equal to 1, which we're going to call the model space. But we are coming back to later what that actually means. And then we are going to have a state P2, which will define an excluded space. So that means that if we look at the projection operator P, this is going to project out the exact state from the exact state, this specific state here. And then we are going to have an excluded state, an excluded operator. This is a projection operator, which is now just the outer product between two states. And we know that the completeness relation is now simply given by the sum from I equal 1 to 2 of these states I here. And we haven't specified whether these states are one-body states or two-body states. Now, this simple problem here has now as an ansatz a ground state, which we're going to label as a phi 0, which is simply going to be given by this A1 acting on 0. And 0 is just a true vacuum state. And then I'm going to have a state phi 1, which is now simply going to be given by an A2 acting on 0. And we can then, when we now look at these specific states here, we can start looking at this in terms of either particle hole excitations, or we can just think of this as a plain eigenvalue problem, where we now are going to set up our Hamiltonian matrix based on that. So what we have then is that if I take the expectation values now of P with this HI of Q, so this is going to translate into phi 0 with HI and phi 0. We will need this element. We will also need a phi 0 of HI of phi 1. And obviously, we are assuming that this is a emission problem and that this is going to give us a symmetric matrix. So we will only need a phi 1 with H1 and phi 1 here. Now, if I take the elements with a phi 0, for instance, with H0, a phi 0, this is just going to be given by 0, and then I'm going to have an A1, and then I have the operator here, P of epsilon P of AP, acting on A1 dagger of 0. Now, this is a quantity which we are now going to evaluate without thinking of a particle hole representation. We could, however, think of it in terms of particles and holes, but then we would have to redefine a new vacuum state. And we could think of this phi 0 as our new reference state. And then we would simply calculate contributions to the Hamiltonian matrix by studying the same type of expectation values, but now with a new reference state. Now we can just treat this 0 as a true vacuum. And we know that the only possible contractions which we can have here are the contractions where we now contract P with A1 and A1 with P here. These are the only possibilities. And you see now that this gives us a delta P of 1. And the same happens here. And all other contractions have to be equal to 0. So this singles simply out a term which is equal to epsilon 1, as expected. Then we can repeat the same exercise with phi 0 of HI of phi 1. And it's pretty easy to see that this one has to be equal to 0. So you will quickly see, no, sorry, this is actually not equal to 0. Sorry for that. So this is going to be given by 0, and then I have an A1. This was actually H0, which is 0. And then I have a sum over P and Q, and then I have this AP dagger and AQ, and then I have an A2 state acting on 0 here. And in this case as well, the only possible contractions are these ones. So that gives us now a contribution, which is simply equal to G. So this is going to be the non-diagonal element. I need also to look at the case where I am in the same state here. So I take the expectation value of phi 0 with H1. And if we now repeat the same algebra here, we were getting an A1. We have this constant G of P and Q of AP dagger, AQ. And then I have an A1 dagger of 0. And in this specific case, P and Q have to be the same. So what I'm going to get then is simply G again. And it's pretty straightforward to see that phi 0 of H1 and phi 1, oh, sorry, H, not that one, phi 1 here. This one has to be equal to G. This means that we can set up a Hamiltonian matrix, which is going to look like an epsilon 1 plus G. I'm going to have G on the non-diagonal L, and then I'm going to have an epsilon 2 plus G. And this is an eigenvalue problem, which we can easily solve by finding the characteristic polynomial. So we are just going to have to find the determinant of, so if we label this as H, this is our Hamiltonian matrix now. So we need simply the determinant of H minus the eigenvalues of lambda, and we want that one to be equal to 0. Now we can then easily find these eigenvalues. So the eigenvalues then are going to be given by, and I'm going to have an epsilon 1 plus an epsilon 2 plus 2 times G divided by 2 here. And then I have a plus minus. And I'm going to have two terms, obviously. There's going to be an epsilon 1 plus an epsilon 2 plus 2G squared divided by 2 here, minus, and then I have a term 4 here, where I have an epsilon 1, epsilon 2 plus G of epsilon 1 plus epsilon 2 divided by 2 as well. So this is the term, these are the terms inside the parentheses. Now, what I can do now is to rewrite this expression and perform later a Taylor expansion. So I can now single out the specific terms here, and you'll see now that if I square some of these terms here, you will find that we can rewrite this expression here as a term epsilon 1 plus epsilon 2 here divided by 2 plus a term G plus minus. And I'm going to have an epsilon 1 plus an epsilon 2 squared divided by 4 plus a term which runs like G squared here. And now it's this is where I can actually perform a Taylor expansion. And this Taylor expansion will obviously be defined in terms of the ratio between the term G and the single particle energy, or this unperturbed energy or non-interacting energies. If these are single particle states, we would think of these as single particle energies, but they don't need to be single particle energies. So these are energies which we could just call for the non-interacting energies. And normally, as we have seen many, many times in this course, these states correspond to a part of the problem which can be solved exactly, or we can easily find the solution to that problem. We can now reorder this equation by looking at the Taylor expansion of the square root. So if we now put epsilon 1 plus epsilon 2 divided by 2 as a common factor, we can actually rewrite this equation as an epsilon 1 plus epsilon 2 divided by 2 here. And then we have 1 plus 2 times G divided by epsilon 1 plus epsilon 2. And then we have, if we now focus only on the lowest line state, so let's just keep the minus sign. And then we can rewrite everything here as a 1 plus, and then I'm going to have a G, and this is now multiplied by a factor of 2 here, divided by epsilon 1 plus epsilon 2, and this term is obviously squared. This is our expansion, which we now are going to Taylor expand. So if we then define x in terms of 2G of epsilon 1 plus epsilon 2 squared. Then we can use the standard general binomial formula and then simply perform an expansion. And we know that 1 plus x, if we expand it, this is just 1 plus x divided by 2 minus x squared divided by 8. Then we have plus x cubed divided by 16, etc., etc. Now, if we just focus on the 2 to 3 first terms here, and we then reinsert x here, this is simply 1 plus, and then I'm going to get 2 times g squared divided by epsilon 1 plus epsilon 2 squared, obviously, since this is now the squared quantity. And then we have x to the power of 2, which is actually 2 times g to the power of 4, which gives us 16 in front of it. So we have a minus 2 here, because we have 16 divided by 18. And then we have g to the power of 4 divided by epsilon 1 plus epsilon 2 to the power of 4. And this goes on to infinity. Then if we now plug these expressions in here, back into here, so you see now that there is going to be a factor of 1, which gives us a factor of 2 here, and then we have a factor of 2 here. And then we are going to have a factor like this one, so divided by epsilon 1 and multiplied by 2 is simply going to give us a g here. We have a factor of a half here, and then that's going to take away this one. It's also going to take away that one. So when we collect these terms, what we are going to get now is something which looks like epsilon 1, epsilon 1 plus epsilon 2 plus this term g. And then if we look back here, we have now a epsilon 1 plus epsilon 2 squared, which takes away epsilon 1 plus epsilon 2 here. We have a factor of 2 here and a factor of 2 there. So that gives us simply plus g squared divided by epsilon 1 minus epsilon 2. And then if we now just stop at the next term, we are going to get rid of one of the epsilon 1 plus epsilon 2's here, because that's going to be taken care of by this one. And then we have this factor here, which takes away that factor. So what we get then is minus g to the power of 4 divided by epsilon 1 minus epsilon 2 to the power of 3. And this goes on actually to infinite order. Now, what we are going to see now is that when we do many-body perturbation theory, this first term here is going to be the first order term. And this term, which you see here, this one, is then going to be our second order term. Now, there is no term which goes like the constant g, which represents some kind of interaction strength to the power of 3. If you look at every term here, if you think of g as something which has dimension energy, we see now that this has dimension energy, this has dimension energy. We have energy squared divided by energy, so that gives us dimension energy. Here we have energy to the power of 4 divided by energy to the power of 3. So everything which we are setting up here has dimension energy. But we are missing a third order term here because we don't have a g to the power of 3. So the term which you see here, this one, is going to be a fourth order term. And by some kind of strange reason, the third order term disappears. We are going to see later what is going to take place here and what is taking place. But this simple exercise which we have done here gives us now an expansion, because we performed a Taylor expansion of this expression here. So I said there's a Taylor expansion around an energy. We Taylor expand it. We get terms to first order in the interaction here. We think of this as an interaction. We get something which is to second order in this term G. We have fourth order in this term G. Everything has the correct dimension, which is energy. And we are going to see that this corresponds to a type of many-body theory, many-body perturbation theory, which is called Rayleigh-Schrödinger perturbation theory. Now, one reason why I introduced this simple model is that I wanted to show you that by performing a Taylor expansion around a specific energy, we're actually going to get an expansion of the exact energy, which is this quantity here, where we now specialize to the lowest line state, and we're assuming that these terms G are larger than 0. And this Taylor expansion is something which we later are going to recognize in terms of a many-body perturbation theory expansion. Now, in order to get started with the perturbation theory, we need to look at some basic equations. And these are the equations which we are going to set up now. So what we have done till now, we now put up the common denominator of many-body perturbation theory. I'm just going to use the acronym PT for perturbation theory, and this is often written as NBPT. So we are going to start with what is called non-degenerate perturbation theory. And what we want now is an expansion for the ground state of the system. You can expand this to excited states as well, but in this course, we will essentially stay with the ground state of the system. And what we have seen now is that we can expand, and now we're just going to rewrite this expansion of the ground state wave function, psi 0, in terms of this unperturbed or non-interacting piece, which is the solution to H0. Just remember that this one has H0 acting on phi 0, and that gives us some energy epsilon 0 of phi 0. So this basis which we have chosen is an eigenbasis of one part of the Hamiltonian. Now, previously what we did was to split this in terms of particle-Hall excitations, but we could now just keep this in a very generic way, and we could think of this as a sum from 1, and in principle, this runs to infinity, but this is going to be truncated at some kind of dimension d. And we are going to have some coefficients, d of m, and then we have this expansion of these new states, phi of m, which are then part of an orthogonal basis state. So what we are going to look at now is to find a recipe by which we now can calculate these different coefficients. And as I mentioned to you, these coefficients d or c or whatever we might call them, if we now spool back here, these coefficients are simply those which we would get from exact diagonalization if we could diagonalize the problem, which is normally not the case because the problem has a dimensionality which is too large to tackle with a standard diagonalization recipe. Now, if you now look at the full Hamiltonian acting on the exact state, psi 0, we have labeled this in terms of an E0 acting on psi 0. So nothing new. And then we have H0 acting on phi 0, which then gives us this non-interacting or often called unperturbed energy. And the total Hamiltonian of the system is simply H0 plus this H of 1, or H of I, which is often written as. Now, what we can do now, since we also have assumed this intermediate normalization, where we now assume that phi 0 by definition is just given by 1 here, we are now going to look at the rewriting of the Schrödinger equation. So we are simply going to go back to the Schrödinger equation here without any time dependence. So we're going to look at time-independent perturbation theory, and we're going to rewrite this equation now slightly. So let's take a closer look at these expressions. So if we take the Hamiltonian acting on psi 0, we are now going to multiply from the left with phi 0. And this is what we did when we constructed that expansion from full configuration interaction theory. This is exactly what we did previously. And this is the same as E0. And then we have defined this overlap to be equal to 1 of psi 0. So this is going to be equal to E0. So nothing special here. We also have a similar equation, which we are going to set up. So we have H0 acting on phi 0, and this is going to be given by our epsilon of 0. So we have assumed also that H0 is an emission operator. So that means that if I were to take phi 0 of H0 of psi 0, then this, and since these eigenvalues are real, this is simply given by psi 0 of psi 0. And we have used intermediate normalization, and we assume that this is equal to 1 then. Now, if we then collect all the terms which we have, what we have then is a phi 0. And we can now keep, if we want to, if we haven't said anything about intermediate normalization, we could keep that term. So that means that we would simply get an epsilon 0 times a phi 0 of psi 0. And if we now subtract this equation here, this one, from the equation which we set up, if we now subtract this equation here from this equation, what we get then is an expression for the interacting part of the Hamiltonian. So if we take now subtract this one from the equation for H, the full Hamiltonian, what we get then is that we take phi 0 of H of psi 0 minus phi 0 of H0 of psi 0. And it's pretty obvious to see that this has to be equal to the ground state energy minus epsilon 0. And then we have phi 0, psi 0. And this is also equal to phi 0 of H1 of psi 0. So then we have an expression, and we actually have, the only thing we've been doing now is to simply reshuffle terms. So there's nothing new which we have done. So if we then look at what we have, we can now divide by this normalization constant. So we have epsilon 0, the exact ground state, minus this non-interacting piece, which is simply given by this expression here. And this is the expression which then will serve as a starting point for doing perturbation theory. So we have a phi 0 multiplied with a psi 0. So this is an exact result, and it's actually independent of the normalization of psi 0 and phi 0. And it's going to be the starting point for generating the exact solution in terms of a perturbative expansion. So what we're also going to do now is to use this trick with intermediate normalization. And we're going simply to assume that this is equal to 1 and psi 0 or phi 0 is also equal to 1. If we do that, then we have that this delta of E, and now we have to be a little bit careful here, because the correlation energy we are defining now is different from the one which we had when we discussed Hartley-Fock theory and full configuration interaction theory, because now we are going to define this one in terms of an E0 minus epsilon 0. And now I'm going to put a subscript 0 here. because it refers to the ground state, but also because I want to distinguish it from the one which we defined when we did the full configuration interaction theory. So I want you to notice this difference, because you see that when we did full configuration interaction theory, we had the exact energy here, but then we subtracted the full reference energy. Whereas when we do perturbation theory, we are now going to make an expansion around the non-interacting energies, which means that we are going to replace this quantity with the non-interacting energy, which we call for epsilon zero. So which is then the expectation value of H0. And that's why I put this subscript here. So that means that when we want to relate the equations which we get from many-body perturbation theory with what we set up for full configuration interaction theory, we have to be a little bit careful when we are comparing terms. And this way of defining the correlation energy is also the way we are going to use when we deal with coupled cluster theory. So let's go back to perturbation theory and do some simple rewrites of this equation. So everything which we have here is just exact. There is nothing particular here. And what we see now is that this term with intermediate normalization is nothing but phi 0 of h phi and then psi 0 here. So this is just a exact rewrite of the equations. So again, there is nothing new here. We're also going to define an effective or model space. And this is going to be defined by this projection operator, which acts on the exact solution, and that projects out the ansatz which we have made for the ground state of the system. And this space P, or this operator P, is an operator which is idempotent, as we have defined before. So this is simply going to be given by phi 0. So this is the outer product here. And its complement is then defined by Q. We also have that P squared is equal to P. And Q is then defined as the sum from m equal 1 in principle to infinity, but we are just going to put this one equal to D. And then it's now given by these remaining states. This is normally called the operator, M here. This is normally called the operator for the excluded space, or the complement of P. So this is normally called the excluded space. So we have degrees of freedom, which we now are going to take into account in a perturbative expansion. This operator which we have here, this one, this defines what we normally call the model space. Or another name for it is just an effective Hilbert space. So with perturbation theory, we can actually set up a formal way by which we can link the model space with the degrees of freedom of the excluded space. And these degrees of freedom are degrees of freedom which we will gradually insert through a perturbative expansion, which is nothing but a Taylor expansion around a specific energy. So you see also that when we deal with these different methods, many-body perturbation theory represents a mathematical algorithm which is based on a Taylor expansion. FCI is simply performing a diagonalization of a Hamiltonian matrix. Hartree-Fock theory was us solving a set of coupled nonlinear equations. And you will also see that coupled cluster theory corresponds to us setting up a set of nonlinear equations which are coupled. So we have now defined an excluded space and a model space, or just Q space and P space. These operators have the nice feature, and this is easy to see actually, and I leave that as an exercise, that these two operators commute. P squared, as we mentioned, is equal to P, and Q squared is equal to Q. And the two together, P plus Q, represent our completeness relation. Now, so what we have done now is to assume that there is a model space which is one-dimensional, and it's non-degenerate, so there's a unique eigenstate here. So if we now look at the exact solution, this is simply going to be given by P plus Q acting on psi 0, which I again can write out in terms of phi 0 plus Q multiplied with psi 0. So we can now use that one, this last term here, to rewrite Schrödinger's equation. So if we now look at Schrödinger's equation, what we have is an H0 plus an HI acting on psi 0. And this is obviously equal to E0 multiplied with psi 0. Nothing new here. And then we can rewrite this one in terms of a dummy variable, which is going to be an energy variable, which we are going to specify a little bit later. So I can simply add and subtract here a variable. So this equation, which you see here, is something which I now can rewrite in the following way. So I'm just reshuffling some terms. So I'm going to have an omega minus H0 acting on psi 0. And this is going to be equal to the same term omega. So I'm just adding and subtracting. Minus E0 plus HI acting on psi 0. So this is me simply taking this expression here and just adding a constant to my expression and isolating the H0 term and the HI term on each side of the equation here. Now, one of the reasons why I'm doing this, after I have defined this term, is that this term here leads to something which we know the eigenvalues of. So let's now bring back the, or rewrite this equation. So one thing which we are assuming now is that the inverse of omega minus H0, so H0 is an operator as well, but that one exists. So we want to write it as omega minus H0. So this is a matrix. If H0 has is given by a matrix. So we can then rewrite this psi 0. So we assume that this inverse exists. So I can then rewrite everything in terms of omega minus H0. And then I have omega minus E0, which is the exact energy, multiplied with psi 0 here. So again, this is an exact expression. Then I multiply from the left with Q. And the thing which I have to be a little bit careful with now is obviously that if I take Q times H0, so let's put hat on these quantities just to distinguish them from just some scalar numbers or some numbers. Now I know that this one commutes and that follows from the definition because H0 acting on phi of I is given by one of these states, epsilon I times phi of I. And Q and P are defined in terms of these operators, of these states. So I have P of H. So it means that the commutator here of H0 and Q is equal to 0. And the same with the commutator between P and H0 is also equal to 0. So that means if I now were to Taylor expand this quantity here, then I have to multiply this quantity H0 with Q. So I can actually rewrite this one in terms of Q multiplied with omega minus H0 is actually the same as Q of 1 over omega minus H0 times Q. But we know that the Q squared is equal to Q, and we often just rewrite this one as Q divided by omega minus H0. So this expressed because Q commutes with H0. So I can rewrite my exact expression now in a slightly more complicated way. So I get plus, and then I have Q divided by, so you may ask, well, what is actually the advantage of doing that? The advantage is that we can start setting up an iterative scheme by which we are going to calculate the final eigenfunction and the final correlation energy. Minus E0 plus H of I, and this is acting on psi 0. Now, what I can do now is to iterate the solution by replacing the psi 0 on the right-hand side with the pi 0, and then I can iterate that solution, and then I can insert on the right-hand side the term. So I start with replacing on the right-hand side, I replace psi 0 with phi 0 here, and then I have an approximation, and then I would place that new approximation back again, and then I would continue like that, so that at the end, I can start with that iterative start. I can rewrite my equation for psi 0 in terms of a sum from n equals 0 to infinity. And then I have my Q of omega minus H0 multiplied with omega minus E0, the exact energy, plus H of I to the power of n, acting on phi 0. And then I can find, if I now multiply with the interaction, so if I look at the term phi 0, which we had previously, of Hi multiplied with psi 0, which defines the correlation energy, where I have the subscript 0 to indicate the difference between full FCI and perturbation theory, then what I have is this sum here. So we have a phi 0 of H multiplied with Q of omega minus H0. Sometimes I forget the hats here. And then I have an omega minus E0 plus H of I to the power of n multiplied with phi 0. So what we have arrived to is something which we are going to call a perturbative series of psi 0 and this delta E0, which has as a basis the solution to the non-interacting problem given by this state phi 0. For these to have a kind of practical solution, or give us a practical recipe, we need to specify this variable omega. And when we have specified that one, we are going to get two types of perturbative expansions. One which is called Brienne-Wigner theory, and another one which is called Rayleigh-Schrödinger perturbation theory. And the Rayleigh-Schrödinger perturbation theory is the one which is normally used because that is going to allow us to rewrite all these terms in this series in terms of known quantities which can be calculated. But this is going to be the topic for next week.